All right, welcome back. Now let's continue our discussion on hypothesis testing. So the first example that I have here is hypothesis testing for inference on mean, assuming that the variance is given to us. Now, I would first talk about a general method for performing hypothesis testing, and then I'll talk about something that is familiar to you, which is p-value. So in general, when you're doing a hypothesis testing, let's say mean is unknown, of course, because we are doing hypothesis testing on mean, but the variance is known. And then you collect some random sample. Let's say the size of this random sample is n, and then we're interested in testing the following hypothesis, where h0 is mu equals to mu0, and h1, or sometimes people also like to write this as ha, alternate hypothesis. The first step is to compute the test statistic, which is in this case z0, x bar minus mu0 divided by sigma divided by square root of n. And number two, you would compute the critical value, which is equal to z alpha over 2. And then finally, if z0, or absolute value of z0, is greater than z alpha over 2, then you reject the null. And then this gives you a general procedure for conducting hypothesis testing. Now, in many cases, you're okay, you're welcome to use this method, but another method that we strongly use many times is based on p-values. Now, p-value, let's define p-value. P-value is essentially the probability of observing a test statistic. This test statistic is basically what we just computed, z0. Okay, so it's the probability of observing a test statistic that is more extreme, than the current test statistic. Right? So it basically says, let's say you've computed your current test statistic 0, and if you get more data in the future, what is a probability, or what is a likelihood that you might obtain a test statistic which is even extreme than z0, right? And so the conclusion that we make using p-value is that the smaller the p-value is, the more evidence you have against the null hypothesis. Right? And so we usually say that if p is less than some significance level, where alpha is your significance level, then you reject the null. Right? So as p gets smaller and smaller and smaller, you have more and more evidence against the null. Since you have more evidence against the null, you decide to reject the null hypothesis. Right? So we can use this regular general p-value approach for performing hypothesis testing. And over the course of next few slides, I'm just going to walk you through some general examples of hypothesis testing, and simultaneously we'll also do some examples. All right, so just to summarize, the very first hypothesis testing on mean, mu is equal to mu0. In this case, your alternate hypothesis was mu not equals to mu0. And then let's look at the two methods. The first method, the general method that I talked about, is usually called a rejection region method. rejection region method. And then what we just looked at a few minutes ago was p-value method. Okay, so you can use either of these two methods to do hypothesis testing. All right, so the first one is HA mu is not equals to mu zero. In this case, the rejection region is absolute value of Z0 greater than Z alpha over 2. P-value is 2 times 1 minus phi of absolute value of Z0. Second case is when mu is greater than mu zero. In this case, rejection region is Z0, not absolute value, Z0 greater than Z alpha. This is where you reject the null, and then the p-value is 1 minus phi of Z0. And then the last one is HA, mu is less than mu zero. In this case, Z0 is less than Z alpha is the rejection region, and p-value is phi of Z0. Right, and we already know Z0. Z0 is equal to x bar minus mu divided by sigma over square root of n, actually mu zero. And then if p-value is less than alpha, then you reject the null. All right, let's do an example based on this. And this is an example that we have seen in the previous exam, in the previous context. The response time of a distributed computer system is an important quality characteristic. The system manager wants to know whether the mean response time to a specific type of command exceeds 75 milliseconds, right? So you can say that H0, this is mu equals to 75, HA is mu greater than 75. From previous experience, he knows that the standard deviation of response time, sigma, is 8 millisecond. And then type 1 error, this should be alpha. Alpha is 0.05. Now to do hypothesis testing, you can use rejection region approach, or you can compute p-value. But either of these two methods would require you to compute the test statistic, which is x bar minus mu divided by sigma over square root of n. X bar is actually available from the last time when we did this problem. So I'm going to scroll there, and this was the problem. And then X bar is given to us as 79.25 milliseconds, and N is 25. Right, so returning back, let's plug these numbers in. You plug in these numbers, you get 79.25 minus 25, sorry, not 25, 75, divided by 8 divided by square root of 5, which gives you 2.66. And now you can compute p-value equals to 1 minus phi of Z0. Since this is a one-sided hypothesis testing, we're using that p-value corresponding to it. And then if you plug in the numbers, you will get 0.0039. Now, if you see, this p-value is actually less than alpha, significantly smaller than alpha. So since it is less than alpha, we reject the null. All right. Okay, now I'm going to walk you through some of the general hypothesis testing cases, and then we'll just look at some of the formulas. All right, so let's look at the first case where we don't have, where the variance is unknown. I think I'm missing some of the slides. Okay, it seems some of the slides got replicated. So maybe what we can do here is we can skip these slides. So we can cancel this, we can cancel this, we can cancel this, cancel this, and then this is the problem that we have just done. So it seems there was some repetitions. But now we are back here. So let's start with the case where this standard deviation is unknown, or the variance is unknown. So when the variance is unknown, our test statistic is denoted by T0, and then this is equal to x bar minus mu 0 divided by square root of s square divided by n. That's your test statistic. Right? Once you have the test statistic, let's write down our hypothesis testing. H0 in this case is, again, mu is equal to mu 0, and then you can have three different scenarios. The first scenario is HA mu is not equals to mu 0. Second scenario is HA mu is greater than mu 0. And then the third scenario is HA mu is less than mu 0. Right? And now let's look at your test statistic. Maybe let me write it down on the left-hand side. This is equal to x bar minus mu 0 divided by s over square root of n. And then you have rejection region. And then you have p-value. Okay, so your rejection region is absolute value of T0 greater than T subscript alpha over 2 comma n minus 1. Value is 2 times 1 minus uppercase T n minus 1 T0. I'll tell you exactly what these, how to compute these numbers, but let me write down the formula first. T0 is greater than T alpha comma n minus 1, and then 1 minus T of n minus 1 T0. And then the last one is T0 is less than T alpha comma n minus 1. And then the p-value is uppercase T n minus 1 of T0. Okay, so now you have two things here. You want to compute T alpha comma n minus 1. This is nothing but inverse T on your calculator with 1 minus alpha comma n minus 1. Okay, and then uppercase Tn minus 1, this is equal to TCDF negative infinity comma T0 comma n minus 1. This is on your calculator, right? So now let's do a quick problem based on this example where your variance is unknown. So in this example, let's say the example says rubber can be added to asphalt to reduce road noise when the material is used as pavement. The sample mean viscosity for 15 specimens of asphalt paving material is 3210.73. So you know the sample mean viscosity with a sample standard deviation of 117.61. To be suitable for the intended pavement application, the mean stabilized viscosity should be equal to 3200. Okay. So we are testing a hypothesis whether the mean stabilized viscosity is equal to 3200 or not. So your null hypothesis is mu equals to 3200. Alternate hypothesis is mu not equals to 3200. And then your x bar is given to you as 3210.73. And then you have n equals to 15 specimens. And then you have standard deviation as 117.61. Now, clearly it says sample standard deviation, right? Since it's a sample standard deviation, we have to use a t-test in this case. So we'll compute T0 first. T0 is equal to x bar minus s divided, x bar minus mu divided by s over square root of n. And if you plug in all of these numbers, you'll get T0 as 0.3533. And now you can compute your p-value. Since it's a two-sided hypothesis testing, the p-value is 2 times 1 minus uppercase T n minus 1 absolute value of T0. And then we know this uppercase T. Uppercase T is basically your TCDF. So let me create some space here. Okay, so now on your calculator, you can do 2 times 1 minus TCDF negative infinity comma 0.3533, comma 14, n minus 1, right? And n is 15. So if you do this on your calculator, you should get 0.729. Now in this case, p-value is not smaller than alpha. And since it is not smaller than alpha, you fail to reject the null. Okay. All right. Now let's do a few more instances. The second instance is, so far we have done inference on a single population. How about making inference on two populations? And usually what happens in this case is we're interested in testing whether the mean value from two populations are same or different. So what we can do is we can define a hypothesis H0, where I'm going to say mu1 minus mu2 is equal to delta 0, right? And then your alternate hypothesis can take three different forms. The first one is mu1 minus mu2 is not equal to delta 0. Second one is mu1 minus mu2 is greater than delta 0. And then the third one is mu1 minus mu2 is less than delta 0. Right? And then in this case, let's write down the rejection region, and then let's write down the p-value. So your rejection region, and then p-value. But before we do that, we need to know what the test statistic is, right? So I'm going to write down the test statistic is Z0 in this case, because we are assuming sigma is known. So test statistic Z0 is x1 bar minus x2 bar minus delta 0 divided by square root of sigma 1 square divided by n1 plus sigma 2 square divided by n2. All right, and now we can write down the rejection region. It's pretty straightforward. First one is absolute value of Z0 greater than Z alpha over 2. P-value is 2 times 1 minus phi of Z0. Actually, it's absolute value of Z0. So let me correct this. Absolute value of Z0. Then you have in the second case, Z0 is greater than Z alpha. And then the p-value is 1 minus phi of Z0. And the last one is Z0 less than minus Z alpha. And then your p-value is phi of Z0. All right. So that's pretty much similar to what we did for a z-test, right? Because sigma is unknown. Now, if sigma is unknown, we can again rewrite all of this using t-statistic. So maybe let me copy a few things from here because this would remain same. So the situation is exactly same. The only difference now is that your sample variance, or your population variance is unknown. So your sigma is unknown in this case. Right? So if sigma is unknown, what we have to do is to use a t-test, just like we have done in the past. So let me write down here rejection region, and you have p-value. In this case, your test statistic is t statistic, which is t0 equals to x1 bar minus x2 bar minus delta 0 divided by sp square root of 1 over n1 plus 1 over n2, where sp is a pooled standard deviation. Pooled standard deviation. And the formula for sp is equal to square root of n1 minus 1 times s1 squared divided by n1 plus n2 minus 2 plus n2 minus 1 times s2 squared divided by n1 plus n2 minus 2. Okay? That's your pooled standard deviation. And now we use just a regular t-statistic or a t-test. So your first case, absolute value of t0 is greater than t alpha over 2, comma n minus 1, and p-value is 2 times 1 minus uppercase tn minus 1 absolute value of t0. Second is t0 greater than t alpha, comma n minus 1, 1 minus tn minus 1 t0. And then the last one is t0 is less than negative t alpha, comma n minus 1. And then the p-value is tn minus 1 of t0. Again, this tn minus 1 is your tCDF. All right. Now, the last one is, so far we have done inference on population mean, but we can also do inference on population variance, right? And in this case, your null hypothesis is sigma square is equal to sigma naught square. And then an alternate hypothesis can take 3 different forms. The first one is sigma square not equals to sigma naught square. Second is HA sigma square is greater than sigma naught square. And then the third one is sigma square less than sigma naught square. Right, so we have 3 cases. Let's look at the test statistic, and then we'll look at the p-values. Okay, the rejection regions are a little bit complicated in this case, so I decided I'll probably skip the rejection region. I'll just give you the p-value because that's easy to compute. The test statistic in this one is called a chi-squared statistic, okay, which is equal to n minus 1 times s squared divided by sigma square, where s square is sample variance. Okay. Now let's write down the p-values. The p-value for the first one is 2 times minimum of chi-square CDF with, actually, let me write it this way, chi-square CDF n minus 1 degrees of freedom, chi-square 0, comma 1 minus chi-square CDF n minus 1 degrees of freedom with chi-square naught. That's p-value for the first case. For the second case, p-value is 1 minus chi-square CDF n minus 1 chi-square 0. And then the last one is chi-square CDF n minus 1 degrees of freedom chi-0 squared. And then this chi-square CDF, this is actually a function on your calculator, which is probably chi2 CDF, if I remember correctly, 0, comma chi0 square, comma n minus 1. That's how you would do hypothesis testing here. I actually have an example here. The example says the output voltage of a power supply is assumed to be normally distributed. 16 observations taken at random on voltage are as follows: 10.3, 9.3, and so on. Test the hypothesis that 8 sigma squared is equal to 1 using alpha equals to 0.05. So we have to test the hypothesis that sigma squared is equal to 1. So the alternate hypothesis in this case is sigma squared not equals to 1, all right? And so now I can compute my test statistic sigma chi-square 0 equals to n minus 1 times s squared divided by sigma squared. This is equal to n is 16, so n minus 1 is 15 times s squared. I computed using my calculator. I got 0.998 divided by sigma squared is 1. So this is 14.970. And if you use your calculator, you can compute the p-value. P-value is equal to 0.908, which is definitely not less than alpha. Alpha in this case is 0.05. So in this case, we fail to reject the null. Okay. All right, so this is a hypothesis testing. Now I want to do a quick review of the 2 types of errors. In most scenarios, type 1 error is given to you, but in some cases, type 1 error is given to you. For instance, in all of the problems that we have been doing so far, alpha, which is a significance level, was the type 1 error. That was equal to probability of rejecting the null given null is true. This is our type 1 error. So in most cases, it's given to us. If it's not given to us, we'll compute it. We'll look at it later. But right now, we need to know how to compute type 2 error, which is beta. Beta is fail to reject null given null is not true. So let's look at this example. Let's say H0 is equal to mu equals to mu 0. Actually, let's say H dot dot. And then HA is mu not equals to mu 0. Now, if null is not true, which means mu is not equal to mu 0, right? And if mu is not equal to mu 0, can I say that mu is equal to mu of A, which is equal to mu 0 plus some delta, plus some shift in the process mean, right? And so this is called, usually we call it the shift in mean. Shift in mean. And if you know delta, you can compute type 2 error. The formula for type 2 error, beta is equal to phi of z alpha over 2 minus delta square root of n divided by sigma minus phi of negative z alpha over 2 minus delta square root of n divided by sigma. So if you know delta, if you know n, which is a sample size, and if you know sigma and alpha, you can compute type 2 error. I have a quick example here that I just prepared. So let's say the content of each coffee can filled on a particular production line is a quality characteristic and follows a normal distribution. We are interested in testing the following hypothesis on the mean content. Okay, from the past experience, it is known that standard deviation of can content is 0.1 ounces. A random sample of 9 cans is to be used, and the type 1 error probability is specified as 0.05. What is the type 2 error probability if true mean content is 16.1 ounces? So it says if mu1 is equal to 16.1 ounces, I can find out mu1 is equal to mu 0 plus delta. So I can find out delta, right? Delta in this case is 0.1. We already know n is equal to 9, right? It's given to us. And then we also know sigma is equal to 0.1. And we know alpha is equal to 0.05. So now I can write down beta is equal to phi of z alpha over 2, which is 0.025, minus delta is 0.1 square root of n is 9, divided by 1, minus phi of minus z 0.025, minus 0.1 square root of 9.1. So if you calculate this, if you calculate z alpha over 2 by the using calculator, plug in the numbers, you will get 0.1492. That's your type 2 error. Now let's, to close this chapter, there's one last little context that I need to discuss, which is the Anova part. Now, we don't talk too much about Anova in this course because it's part of design of experiments, but I do want to touch a little bit on this. So far, we have done hypothesis testing on one population. We have done hypothesis testing on 2 populations when you're comparing 2 different populations. But if you're going to compare multiple populations, more than 2 populations, then you have to use something called an Anova. All right. Now in Anova, there is a typical data structure. It has certain treatments. Think of treatments as different populations. So treatments as different groups or populations, right? If you only had 2 groups or 2 populations, you can use a hypothesis testing on 2 sample means that we have done in a few slides earlier. But if you have more than 2 groups, you have to use an Anova, right? And then in Anova, we usually call this treatment. Actually, in design of experiments, we call this as treatment. Now, when we're doing Anova, the general hypothesis that we are interested in is to see if all of these treatments have the same mean. Okay, so in other words, what we're interested here is H0, which is basically saying mu1 equals to mu2 equals to mu3 equals to dot 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 equals to mu a. All the treatments have the same mean, and HA is mu I is not equal to mu j for some I not equals to j. Right? Now, I am not going to walk you through the derivation of Anova entirely. I'm just going to take you to some of the important aspects of computing an Anova table. Now, to perform Anova or hypothesis on multiple population means, we typically take a 4 to 5 step process, right? The first step is to construct a linear statistical model, where you basically say that every data Yij is composed of a fixed mean, which is mu0, plus there is some variability from treatment to treatment, from group to group, and that is captured by this tau I, and then everything else is thrown to an error term, right? This is basically your error term, error or noise term. And then tau I is your treatment effect. Again, remember, treatment is always different groups, right? So once you have developed this model, now all the data is basically given to you, right? And we just constructed that model. When you have this data, we compute a couple of things. First is yi dot, which is equal to summation of yij, j is equal to 1 to n, yi dot bar, which is now just the average of all of these yij's. So this is equal to 1 over n summation of j is equal to 1 to n yij. And then you compute y double dot, which is equal to summation of your yi dot, I is equal to 1 to n, and then y dot dot bar, this is equal to 1 over a, because you have a total of a treatments, y dot dot. Now, you don't have to do this for any of your assignments or exams. I'm just walking you through the process of doing it. And then you compute a few important terms. The first one is sum of squares total. This is equal to summation of I is equal to 1 to a, summation of j is equal to 1 to n, yij minus y dot dot whole square. This is equal to sum square total. Then you compute sum of squares treatment. This is equal to n times summation of I is equal to 1 to a, yi dot minus y dot dot bar whole square. This is equal to sum square treatment. And then once you have sum square treatment, sum square total, you can compute sum of squares error. This is equal to sum square total minus sum square treatment. Okay. And once you have computed sum squares, now you will compute mean squares. So mean square treatment is equal to sum square treatment divided by a minus 1, and then your mean square error, this is equal to sum square error divided by a times n minus 1. All right, now we have computed everything. So what we do is, whatever we have computed so far, we actually put this on a nice looking table, which is called an Anova table. So the first column is your source of variation, which is your treatments, different groups, error, and total. You have sum square treatment, you have sum square error, you have sum square treatment, sum square total. Sum square total is always the sum of sum square treatment plus sum square error. The third column is your degrees of freedom. The fourth column is your mean square that we have computed. And then last column is F0, which is the ratio of mean square treatment and mean square error. Once you have computed everything, to perform hypothesis testing, you have to test if F0 is greater than a critical value, which is F of alpha, comma, A minus 1, comma, A times N minus 1. Right? And how do you compute this on a calculator? Once you compute this term, you can reject the null, right? This is the rejection region approach. If you want to compute p-value, you can compute p-value equals to 1 minus f CDF 0, comma, f0, comma, a minus 1, comma, a times n minus 1. That's what you would do on a calculator. And then you can get the p-value. And if p-value again is less than alpha, then you reject the null hypothesis, right? And then I have a quick example here that I wanted to show you quickly. So this is an example where you have 4 different hardwood concentrations. So you can think of 4 different groups of hardwoods. And then you have some data collected, and then you have some totals and averages. Right? Now, I have already done some computations, so I'm not going to repeat the computations, but I'll give you all the details here. The first one is source of variability, which is your treatment, error, and total. The second column is sum squares. So the first one is sum square treatment is 382.79, 130.17, and then the total is basically sum of these two, which is 512.96. If you want, you can compute these numbers as well using the formula that I've given above. And then you have degree of freedom, which is for the treatment, it is A minus 1, A is 4 treatments. So this is 3. Error is A times N minus 1, A is 4, N is, how many observations do we have total? We have a total of 6 observations, right? So 6 minus 1 is 5. This gives us 20. And the total degrees of freedom is just sum of these two, 23. And then you have mean squared. In the first case, your mean square is sum square error divided by degrees of freedom, which is 382.79 divided by 3, which is equal to 127.60. Then you have for error, this is 6.51. And then finally, you can compute your F value, F0, which is 19.61. It is basically the ratio of mean square treatment and mean square error. Now, finally, we can compute p-value. P-value is equal to 2 times, p-value in this case is just 1 minus f CDF. You have your test statistic, which is 19.61, 3, 20. And this is equal to 3.59, 10 to the power minus 6. And since this is less than alpha, actually very, very less than alpha, so we reject the null. We reject the null and we conclude that hardwood concentration does affect the paper quality, which means there is difference from one treatment to the next treatment. All right, so this is end of chapter number 3. I will stop here and see you all next time. Thank you.